Hello, everyone. Welcome. My name is Iakymchuk, and I will be co-hosting this webinar together with my colleague Pablo de Oliveira Castro from Université Paris-Saclay. And before we start with interesting part, I would like to provide some overview of the project. So this Center of Excellence in Exascale CFD, and more specifically, what we are doing, we try to model complex phenomena as turbulence, and in this project, our focus is on algorithms, in improving algorithms and energy efficiency. So this would be the focus of this presentation. In terms of improvement of algorithms, we will focus on mixed precision in terms of, and how it actually correlates to energy efficient simulations. The other two objectives that we settled in a project or set up is exascale ready workflows, and also lighthouse cases as demonstrators. The simulations cover various aspects of turbulence. We have two cases on shock in terms of incompressible Navier-Stokes equation, shock boundary, layer interaction. So this is more specifically to this buffet of wings and the source of turbulence, and as well as strengths of materials. There are also a couple of simulations related to topology optimization in terms of static mixer, as well as merchant hull, ship hull simulations, this Japanese ship hull with big sort of turbines. We are also covering a simulation of atmospheric boundary layer with high Reynolds number, as well as erosion of offshore wind turbines with on the seabed of Baltic Sea in northern Germany, which is applicable to other simulations. So this is what we are doing, and here the focus would be pretty much related to NECO simulation. And at this point, I would like to pass a pointer to my colleague Pablo, who will introduce how we can use tools in order to enable mixed precision, and then I will continue with the results. So Pablo, please share your part.
So, yeah, as Roman introduced, I'm going to speak mainly about VerifiCarlo and the methods it uses as a tool, and it has two main objectives. The first one is to detect numerical instabilities, but it also allows to explore the effect of using reduced precisions. So in fact, if you want, before porting your code to mixed precision, to see the effect it has on numerical errors, then it allows you to estimate that empirically. Okay, so just a slide on context. So we all know HPC AI is quite energy intensive. If we take a top HPC system Frontier, it has exaflop performance, true exaflop performance, but it consumes 21 megawatts, which is the power required to power a small French town. So it's quite big, actually. In the context of CEEC, we know that computational fluid dynamics requires massive scale. Question is, can we reduce precision? Can we use the new floating point formats that are pushed by mainly by AI and GPUs to improve energy and time to solution? It seems like a good idea, but floating point arithmetic has many challenges. And well, I'm just going to mention them, but I think many of you are familiar already with this. We have errors that can happen at all, let's say, all the steps on our numerical design pipeline. First, when we model physical phenomena, we already have to choose some kind of simplification, mathematical simplification. So we are going to have an approximation, we are going to have discretization, we are going to have conditioning. And then we get into how real numbers are implemented in the computer. So we have a very nice standard, IEEE 754. But because it's a finite representation, we can have, well, representation issues, absorption, cancellation, and it's quite sensitive to the order of operations. So when you start parallelizing, vectorizing, passing your code through an optimizing compiler, you can get all kind of unpredictable effects. So we have this tension, this compromise between low precision and accuracy. Okay. So first, just a quick word on vocabulary, just to be on the same page. So there is a standard for metrology. So imagining we have a computed measure, for example, a repeated measure, so a repeated computation. We can define the precision, and that's how close our different samples, trials are. Then you have trueness, and then you are saying, are the samples around a reference? And then you can have both, and that's precision plus trueness, which is accuracy. And then you are both precise and you are around the reference. The tricky thing is we don't always have a reference value. Sometimes we can have physical simulations with different modes or that admit different solutions. And sometimes we are working on a new simulation, or we're debugging a big simulation and we are only working on one piece of the code, and we don't necessarily know what is the mathematical or physical exact ground value for computation. But what we are going to show in this presentation is that you can already check precision and reproducibility without a reference in many cases. Okay. So floating point arithmetics. So we have this standard, and here I'm just giving one example about absorption. So we have two floating point numbers. One has a big, in 32 bits, one has a big mantissa, a big exponent, and the other one a small one. So you see the two exponents have 20 bits difference. So before doing the sum, we have to put the two mantissas under the same exponent. So we are going to shift the mantissa of the smaller value, and all the digits in red are going to be lost because we don't have enough hardware bits to keep them. So usually our error model, when we want to model that and compute the error, is based on the guarantees of the standard. And the standard tells us that for the basic operations, we are going to have a relative error that is going to be less than half the unit in the last place. And the unit in the last place is the distance between two representable numbers. Okay, so we can intuit this visually for those who haven't seen this. If we have the exact value z, and you see we have to choose to round either to the floor or to the ceiling. The default rounding mode is round to nearest, and in that case, we are going to round down. And you can see that the worst case is when we are just exactly between two representables, and then we have u divided by 2 as error. Okay, so that's the standard deterministic round to nearest behavior. The thing is, this is deterministic. So you have your program, you're going to run it multiple times, and except if your program has some kind of Monte Carlo going on or indeterminacy, you are always going to get the same result. And you don't know how precise this result is. So a different way to model things is with stochastic arithmetic. So stochastic arithmetic is something that has a lot of history. Actually, already there was some trials of stochastic arithmetic in the ENIAC, so it's quite old. But the first time I found stochastic arithmetic was through the work of Stott Parker in '99. And the idea is, instead of modeling deterministic rounding errors, you are going to model errors as random variables. Okay, so you're going to have a computation. You are going to chain, for example, here, plus, plus, and multiplication. Each operation is going to have one error. And we are going to model the errors, delta 1, delta 2, delta 3, as random variables. So we can model the forward error, see? and we can analyze it probabilistically. So we have a stochastic process that is function of the chain of errors. So here we can have different choices for our distribution. And one very good choice is what now in the literature we call stochastic rounding. So the idea of stochastic rounding is to round inversely, with a probability, sorry, inversely proportional to the distance to the representant. So let me introduce this with an example. Let's say we are on base 10. Let's say our true result is 1,62. So we can run down to 1,6, or we can run up to 1,7. The idea is we are going to run down with a probability of 80% chances, and we are going to round up with a probability of 20% chances. Because this is our binomial probabilities, we can compute the expectancy, and in fact it's going to be 17,02 times 0.2 plus 16 times 0.8, and we get as average the exact mathematical result. So that's very nice property. In fact, stochastic rounding gives you for one operation an unbiased distribution. So the average of many samples is going to give the exact result. So we have extended this property to a chain of operations. And Mediel RR, who did his PhD at UVSQ, and following results by Connolly, Murray, and Hayem, show that actually if you have an algorithm that you can write as a sum product computation graph, so you can put plus, multiply, but there is one constraint, is it must be linear. So in fact, you cannot multiply two operands that have a common error term. But this already covers many algorithms. If you have this kind of computation graph, then in fact, you can show that the total error of the algorithm is a martingale, which is a generalization of a random walk. And this has very powerful properties. We can show that actually the total computation error is unbiased. And we can also bound the error by square root n, which is the number of operations, u, which is the unit in the last place. And this is much better than the worst case linear bounds that we get when we use deterministic rounding, which are in nu. Okay. Okay. So applying these results to many different algorithms, we can get bounds on the errors. And that's quite nice. You see dot product, polynomial evaluation, pairwise summation, Karatsuba multiplication. And we always get this square root gain. Okay, but how can we use this on real codes? Because it's very nice. This gives very nice properties for a small computation kernel. But when you get a big Fortran code, big C++ code with thousands of lines, how can we model things? Well, one idea is actually to use stochastic rounding as a model of deterministic rounding to see what happens with your IEEE code. We have to be careful. We always have to compare against IEEE round nearest to detect stagnation, because stagnation is the property that actually explains these cases where ESER, stochastic rounding, and deterministic rounding, round to nearest, are different. But in fact, we can use this randomness as a model of error. And how do we do this? With a very big algorithm, we cannot do the formal analysis. Okay, so we can use Monte Carlo simulation. And that's the idea of VerifiCarlo. So in VerifiCarlo, we are going to take an algorithm. We are going to run it many times with stochastic rounding. Okay, so the errors are going to be random. And at the end, instead of getting one deterministic result, we get a distribution of results. And in this case, I have computed a small 2-2 system, which is ill-conditioned, and I have taken 10,000 samples. And if we print the first 3 samples, we can see that they have a set of numbers in common, and then they have the tail of the mantissa that changes each time depending on the rounding errors. So if we plot the error distribution here, we can see that actually the significant digits we get is in fact linked to this ratio, and this ratio is the signal to noise ratio, actually. And this is shown by Stott Parker in the reference I gave before. And we have actually studied this in more depth, and we have shown actually that we can provide confidence intervals, but this quantity appears on those confidence intervals. This quantity is central. And you see here we get 28 significant digits, and that's exactly, in fact, linked to the condition number in this example. Okay, so how to do this automatically, transparently? We provide an open source tool, which is the VerifiCarlo project. It's on GitHub. Now it has more than 10 years. It's an active open source project with 15 contributors. The main contributors are from UVSQ, Concordia University in Canada, Intel. And the idea is we leverage the LLVM compiler. So we take any code that the LLVM compiler can compile, and we are going to replace all the floating point operations by callbacks to specialized backends. And those backends provide alternative floating point models, and in particular, stochastic rounding. We repeat, for example, for stochastic rounding many times the runs, we get the samples, and then we do a statistical analysis to get the precision of our code. We can also actually, with stochastic rounding in our backends, change actually the virtual precision. So we can simulate smaller precisions, and we also have backends that simulate round to nearest in lowest precision. That's where we get into mixed precision. One thing that is nice is because this is done at the compiler level, in LLVM, we do the instrumentation at the very end of the optimization pipeline, just before code generation. So in fact, we can capture what the compiler is doing to our numerical code. In this example, I have a compensated can sum, which is a way to do summation recovering small absorption errors. And I'm not going to explain it here in the interest of time. But what is funny is if you activate in the compiler fastmath, which allows you to reorder all floating point operations, the compiler is going to optimize that and is going to produce a very efficient code, but which does a naive sum. And we can see this because when we run this in VerifiCarlo, if we compile in no0, we get a very good, we get a small error. You can see here, we have 7 digits that are correct. 7 decimal digits, and this is in float precision, so it's quite good. And if we activate fastmath, we break the can compensation term, and you can see that we lose 2 digits of precision. Okay, so what kind of backends do we have? I'm not going to get into many details, but we have stochastic rounding analysis. We have this is the kind of legacy backend, but for 2 years now, we have a new fast vectorized stochastic rounding, which is called Prism. I'm going to introduce it in next slide, which is much faster, and it gives numerically the same results. Then we have vpreg, which allows to emulate variable precision, and we have one backend for cancellation. Those are the main ones. There are a few more, but that's the more interesting ones. And then we have some tools that are orthogonal to this. For example, we have Delta Debug that allows you to use these backends to localize precisely in the code where some bug is happening or which part of the code you can move to a lower precision. So this Prism backend has been initially developed by Johan Chatelain, and you have the reference of the paper here. They have based on VerifiCarlo, they have a very nice image which is called the fuzzy ptorch, which allows to run ptorch using stochastic rounding to actually understand what is the effect of rounding and what is the effect of precision on deep neural networks. So for this kind of computational expensive codes, they really needed to have a fast backend. So they leverage Google Highway, which is a library that allows to implement stochastic rounding using vector instructions. And they have done very nice work to improve multi-thread performance. And what we can see is that here, for example, they tested on this paper on different deep neural networks. So MNIST, which is quite well known for recognition of numbers, handwritten numbers. FastSurfer, which is for neural networks, for neuroimaging, brain imaging, and WebLM, which is for speech recognition. And you can see that VerifiCarlo with the Prism backend has an overhead. You are going to be from 10 times to 50 times lower, but you can emulate this stochastic rounding transparently. And this can have practical impact. They use that and they show that on FastSurfer, which is used for brain imaging, there were numerical instabilities. And it was interesting because it was on a part that wasn't important for brain diagnostic. So they could actually enable code shortcuts, yielding efficiency gains. That's their work. So if you have any questions on that, you can write Inés González Pepe, and I'm sure she will be very happy to explain the details. So I'm going to finish before giving the hand to Roman on VPREC backend. So VPREC allows to safely explore lower precision. So you can do that with stochastic rounding, but you can also emulate what is happening with standard IEEE 754 round to nearest. So we can emulate FP32, bfloat16, TensorFlow32 on standard hardware before doing the porting. We deal with that by doing an emulation, and we handle all the tricky cases like overflows, underflows, denormals, not a number, and we provide round to nearest, faithful round to nearest. We have a small overhead. We are going to be from 3 times to 70 times slower. And we can simulate any format that fits in the underlying hardware format. So for example, if we have a float, we can simulate binary 16 by reducing the exponent and reducing the mantis. So just one slide to explain how this works. And we can do this both in stochastic rounding and in round to nearest. So the idea is we are using, there are different techniques, but in the Prism backend, for example, the way we do it is we use error-free transformations using FMA to compute our operation in extended precision. So we get a couple of values, actually. And so we are going to have our result X, which is equal to sigma theta. So first we are going to truncate to simulate a lower precision. So here you see we are here on the red point, exact X. We truncate to the lower representative. And then we look at the error. And the error between the truncation and our point is going to have 2 components. The virtual truncation, that's to say what we lose because of the virtual precision, and the hardware error, theta here, which is computed with the error-free transformation. And then, I don't know if you remember, but for stochastic rounding, we have to round down with a probability inversely proportional to this distance in pink. Sorry for that. I hope you can get the PDF after the presentation if you want to look again. I'm going to show quickly, but 13 was this one I thought you got. This one, I think it's okay. Most of it was understandable. So for this one, yeah, we have the exact number, X here. We truncate. And then we have one error that depends on the truncation, here rho, and we have theta, which is the error that we did in the underlying hardware format. So then we take a random value uniformly, and if the value falls on the pink zone, then we are going to round up, and if it falls outside the round zone, then we are going to round down. And the trick is, if we want to emulate round to nearest, well, we just select P as a constant exactly in the middle of the interval. And this works well, except for ties to even, for the ones that know very well the IEEE 754 format. Okay, one last technical slide. Sometimes we want to combine VPREC and stochastic rounding, MCA. So for example, this is a work we did in 2019 on CFD code. So we found a VPREC configuration in reduced precision on the deflated conjugate gradient solver. And then we simulated it with stochastic rounding to see if it was stable. And here you can see that the 29 samples in stochastic rounding with the reduced precision, they follow the convergence of the reference in IEEE. So that can be a way for the practitioner to test if their mixed precision, let's say, profile is good. One important thing is that VerifiCarlo is only an empirical tool. So it's going to tell you this works, this doesn't work, but it's not going to tell you why, and it's not going to give you a formal proof that it's going to work for any input. Okay, this is for a particular input, and that's quite important. It can be a very good tool when you are doing this kind of studies, but it doesn't free you from looking at the math and understanding your physical assumptions. So I'm going to conclude here. I've shown two backends, stochastic rounding and VPreg. Stochastic rounding mainly for checking accuracy, VPreg for evaluating mixed precision, limitations, costly overhead, data-dependent analysis, and we have poor support of Fortran because we build on LLVM. This is getting better, but be aware there are alternatives. For example, at some point in the slides, I compared to Verou, which is a similar tool, and we share many backends that works with Valgrind. So in cases where it's difficult to compile with VerifiCarlo, you can use Verou. We have worked with different application like IBinit for material science, Yales 2, and also DP, PX, QMCKL. So I'm not going to speak about this because Roman is going to present the work we did with Yang Chan on Neckbone and Neko. So that's me.
Yeah, thank you, Pablo. That was very inspiring. I will continue with my slides. Yes, so, okay. Now I need to, second. Mhm. Yeah, got them. Good. So now I will continue with our methodology and our analysis in SafeDeco. So oh, it's running slides. Oops, just excuse me. What Pablo has shown you was about how to use tools in order to detect abnormalities, to inspect your code, and to analyze your code in terms of also what kind of precision would be suitable. And the VerifiCarlo is actually growing. When we started using it, it had, I think, 3 backends. Now there are 4 backends, and it's super nice. For us, since we are solving compressible and incompressible Navier-Stokes equation, for us was important to determine whether it's possible to use lower precision, because we are talking about reduced mixed precision, and how safe it is to use it. So that's why we selected tools like VerifiCarlo. And the other aspect was that the other way would be to do numerical analysis, prove for different test cases, and then implement for our. And one more, a bit more radical, just try and see what happens. So we decided to go in between theoretical proofs and empirical, and we decided to use tools like VerifiCarlo in order to determine whether it's possible to reduce precision, whether there are any numerical abnormalities, and which kind of precision can be used. So that was our story. Our methodology, we say it for energy efficient computing, but in fact for enabling mixed precision, is as follows. So we set up some accuracy guarantees, accuracy expectations in our solvers. We are solving incompressible Navier-Stokes equation. So we have velocity and pressure solver. Velocity usually runs until 10 to the power minus 7. Pressure is 10 to the power minus 4, minus 5, depends on the test case. And our idea is that we set up, so we try to understand what is a performance bottleneck, not performance bottleneck, performance most consuming part of the code. Then we run our tools like VerifiCarlo through it in order to see how much actual precision is needed. And then if we see what would be the indicated precision, how low we can go in safe sort of modes that accuracy would be delivered, and then we do porting to mixed precision and validation. We have an article about this the article describes Poisson's example. So basically, we were using preconditioned conjugate gradient in NECO ecosystem. Another motivation here why we need to reduce, because we want to have how to say, new algorithm, new optimized, improved algorithms, and higher precision certainly is good. Yeah, we can use it, but there is, and it's more accurate, but it's more energy hungry. Since we were moving towards GPU and we ported all the codes to GPUs right now in the project, now we are working on making a good use of GPUs. And as you have seen from with new generations of GPUs, double precision is getting smaller and smaller. So we wanted to see whether we can switch to single precision, whether we can combine also single precision, and what would be the benefit, and or can we go lower than single? So that's the answer, yes, but we need to be very careful if we go beyond single precision. And lower precision has this benefit that we have more flops per watt. There is another metric that is called more instructions per watt, or more per byte, or something like that. So, or more like bytes per watt, something like that. So, and we will have less smaller memory footprint and less data transfer. So that's the idea, and the methodology based that we look on bulk computations, try to enable lower precision, and then we do correction in higher precision in final result. So this actually connects to the famous, what to say, iterative refinement for LU factorization, when L and U factors computed in lower precision, and then iterative refinement runs pretty much like Newton iterations that improves the accuracy of the simulations. And that dates back to Clive Muller's article from 1986, and also to Wilkinson, even to Wilkinson, that from 4047. Okay, so that's our methodology in a nutshell, and let's move to some more test cases that we were experimenting. We started, our main target is NECO and NEC 5000. So it's high order methods. High order means that polynomial order ranges from 5 to could be even 12, and it's incompressible in our Stokes equations for based on spectral element methods. So it's like a matrix free. And we focus here on pressure, on actually velocity solver, not pressure. We using Jacobi preconditioned conjugate gradient method. We start NECO, since NECO is a big code. We started with something simpler, and it was NECBON mini app that does a similar job but on artificial grid, and but uses multi-grid precondition. So what we did with NECBON is basically CG preconditioned CG. And what we did, we tried to run our VPRAC through NECBON, and on the left side you see a CG loop, and in CG loop we know that there are a couple of sensitive parts, like mainly related to dot products, so steps 2, 6, and 8, and especially we put our focus on step A, so it's computation of residual, and on the right we try to do experiment by changing number of bits in mantissa. Exponent was kept still double precision, and we were trying to observe on axis Y how residual changes. We also use different problem sizes, different number of elements, and the higher is better. And we can see that at some point we have a plateau, so like flat line, and this indicates that more bits we use, the accuracy won't be improved. So it's like that's what we have seen. So, and then we can see that plateau starts from approximately 16, 17 bits. So it means that we can safely use single precision, which is requires 23 bits of mantissa. So this indicates to us, this experiment showed us that we track the variable from beginning to the end. And then we do this through the course of computations. The other strategy would be if we can actually track it per time step or so on. So that could have been another one. So, but this is what we have selected. Then we decided, okay, we were very optimistic, and then decided, okay, let's switch everything to single precision and see how it performs. On the left, you can see that how to say, we try to test MCA backend, and we try to do with two modes, light and more rigorous one. On the left there is a lighter one, and you can see that, oh, seems to be good. Iterations converging very nicely, and yeah, there is no a lot of this sort of noise. But when we looked on the right picture with more rigorous analysis, and we can see there is indeed a deviation, and we were able to pinpoint it that there is due to initialization steps that we have 10 to the power 9 multiplied by cosine. So we decided to focus primarily on the solver, because this is where the major amount of time is spent. And by doing this, we were able to get identical results with both modes of MCA backend, which gave us a green light. So we were very happy with this non-preconditioned case that we can move to single precision on the solver only. That was very fascinating. And then we said, okay, that's very promising. So let's see what happens with preconditioned case. And the picture was not as was quite nice. The preconditioned case. We ran through MCA, and the MCA actually indicated to us that there would be some stagnation at certain point after 10 to the power minus 5 in terms of residual. And here we plot residual over here so that we observe convergence. And this also have been detected when we run with I4 with optimization level. So by exploring further, we decided that, okay, that's the reason for this is we did some exploration with the tool, and we were focused on pairwise mode communication. There is all reduce as well, and we can see we try to see when the problem appears, and in reality what we found that global operations like dot products and gather scatter operation that require some parallel reductions need to be done in higher precision, while computations, CG computations, the other CG computations as well, application of preconditioner can be done in lower precision, and that's our sweet spot. We also discovered that square root has to be done in higher precision, and then we were able to have very good conversion. So our recipe from this large table is that global operations, especially dot products, are very sensitive, and it's better to keep them in full precision, while the other operations, local operations, can be done in single precision. Obviously, when we do this, it requires some casting, and then I will come to that a bit later. In terms of experiments, we did our runs on a Mare Nostrum cluster with Intel Sapphire. We tried to do all possible runs with Neckbone, with precondition, multi-grid preconditioner. So we have double precision against which we compare. A maximum number of cores there were 80, and we can see that it's already clear that pairwise is better in terms of execution time when we look on the last column. In terms of gain, when we use all reduced strategy, we were getting 1.62x speed up in this mixed precision double single strategy, and in terms of pairwise, we were getting 1.36x speed up. And next step, what we did, we tried to measure energy consumption, and was it a story about it. So we prepared best practice guide, which is available on the CEEC project webpage, which is quite nice guide how we can measure energy consumption in different European systems. And we did so, and to our surprise, energy consumption, energy gain was better. We use EAR software that's provided by BSC, the hosting center for Mare Nostrum 5. And we can see with all reduce, it exceeds 2x. So it's a bit, how to say, over optimistic. We sort of granted to to much better utilization of cache, but needs to be explored further. In pairwise, we got 1.48x, 46x speed up. So this was study with Negbon. And having this study with Negbon that was written in Fortran 77, we propagated our knowledge to Neko, which is written in modern Fortran, which was a bit troublesome for us to enable VerifiCarlo due to the poor how to say Fortran support from LLVM. Yeah, so that's but with Neko we propagated our story there, and we can see that we were running on the same machine with -3 optimization flag, and here are two messages that we can draw. We were running until 10 to the power -8, I believe, or 9, and then we can see that global double precision is this dotted blue line, while our mixed strategy is a red line. We can see that we require a bit more iterations for non-precondition and precondition case, but we were able to reach our converging point. And the next step, what we try to do is we have computations in single precision, and then we have to cast data to double precision. We use dot product in double precision, and we cast back. So we said, okay, this is not new scenario, and we try to actually do some sort of emulation. We try to emulate double precision using two single precision values, and here's a result in terms of quality of result on the right-hand side. So we can see this sort of axis in light blue and crosses in yellow. That corresponds single precision, and we have our emulated result for dot product in this crosses in darker blue. So you see that in terms of accuracy, we can emulate double precision accuracy, and we implemented this mechanism called two product. We used idea and some parts of implementation from François Ferrot, and we can see that yeah, in terms of this line, like orange line, we are converging similarly to our winning strategy. However, we are not getting much gain because the vectors are too short. So when vectors would be longer, then the gain would be better. So that's we avoid casting, but we have to pay price for this extra operations that we need to perform for the simulation. So it's yeah, it was a good study, but and a good compromise in order to avoid conversion. And then it worth mentioning here that we lost in terms of full accuracy. We cannot have full double precision comparison. We are losing a bit of mantissa bits, about 6 bits. Okay, and next step, what we did, we also measured execution time and energy. We can see that it was done also in the same system. We can actually cover different system, Lumi and Mare Nostrum primarily, but we are now working on Carolina. And we can see that the best gain what we got in terms of time was around 1.18x, while in terms of energy was 1.22x. So as you see that there is some correlation. We don't have these tremendous gains as in Negbon, and we have explanation for that. So Neko is highly optimized code, and compared to Negbon that was written like more than 10 years ago, and there is and very, how to say, specifically tuned for modern HPC architectures, and there is we didn't have much room to have a bigger gain. Now we have also pressure solver with GMRS, adaptive Schwarz multigrid preconditioned GMRS, and we have the whole complex, and we also mix precision, and we will see how it actually will perform in terms of gain and accuracy on the longer run, when time steps were activated as a full fluid solver. And we also explore something quite interesting, fascinating, how accuracy correlates with energy and time. So we have two plots: upper is energy, lower is time. Obviously, naturally, what we would expect that mixed precision takes lower. So it's like lower is better, and we try to correlate tolerance. So we started with 10 to the power -4 to 10 to the power -10 in terms of time, lower picture, and we can see that yeah, we are lower. gain slightly increases. In terms of energy consumption, we were able to get better gain. And please remember that it's Poisson solver, so basically represents velocity solver, and velocity runs currently that we are using periodic hill runs at 10 to the power minus 7. So the gain here is it's getting larger. And that's something positive that we expected from the full lighthouse simulations at the end of the project. So that's all the results that I have. So the message that we would like to convey, if you have complex codes and you would like to explore mixed precision, try to go with computer arithmetic tools. You already experienced with other tools in terms of detecting, optimizing your communication pattern, etc. But adding arithmetic tool like VerifiCarlo, which also support CI/CD checks, it's a very nice option. VerifiCarlo is not only one tool, as Pablo mentioned, but the tool that we got great support was our choice. And we enable mixed precision in ECBON and ECHO. We use different tools, gprof, VerifiCarlo, InterAdvisor, in order to see where we sit in terms of roofline model. You can see, so we are sitting on this, on this corner when between memory and compute intensive, and we were able to move it with mixed precision even higher in terms of compute intensity. And yes, and we were able to get some relatively good gains. And yeah, more results will come. And I think that something that is really fascinating, what can be done, how to do this precision optimization, because currently we did static from beginning to the end, how to do it adaptive, either between time steps or during the time steps. So it's like quite fascinating. So thank you for your attention, and